Hello, I'm Patty Simpson with Simpson Math. In this video, we're going to create a sampling distribution of sample means. And then we're going to use that to discover the central limit theorem. So first, I'm going to look at an applet. This applet, I'm going to put the link for this applet in the comments of my video so that you can go to this online stat book and see this applet yourself. But this is how this applet works. It's just going to help us to discover and to see what a sampling distribution looks like. So here is some population of data. It's got a nice normal shape to it, that bell-shaped curve that we've been studying about. And so maybe this data is something like women's height. And so we've collected a bunch of data and put it on a distribution, and it has this nice normal curve. Over here we can see the mean of that data. Our mean here is 16. It doesn't work as well with nice women's height, but just roll with me. So there's the mean average of our data. The median, we know in a normal distribution, should be the same as our mean. And then the standard deviation of this distribution is 5. So just for documentation purposes, I'm going to write that down here, that our parent distribution, when it is a normal distribution, when we have this normal shape, see it says shape of the parent population is normal. When it's a normal shape, our parent mean is 16. And then our standard deviation is 5. I'm just going to record that here. In a minute, we're going to do something with it. So now here's what I'm going to do. From that data, that population data, I'm going to take a sample of data. I'm just going to take a sample. Right now, let's start with sample size 5. And so in other words, I'm going to take 5 women and I'm going to measure their heights. And it's going to drop down those 5 women's heights down into this second category here. Then, once I have those 5 women's heights, I'm going to add them up and find the mean of those heights. So I'm going to find the mean of my sample data. And that mean, I'm going to drop down into this third little spot to make a whole new distribution of those means. So let me just show you what I mean. So here I have my population of data. I'm going to drop down 5 women's heights. So see, these are those 5 data points, those 5 random women's heights. And then I found the mean of those 5 women's heights. And that mean I plopped down here. I'm going to do that same thing again. From this parent population, all these women's heights, I'm going to pick 5 of them at random. 1, 2, 3, 4, 5. And then I'm going to drop it down, find the mean of those 5, and drop it down into a new distribution. So this is a mean of my sample data. This is a mean of my sample data. Let's do that again. 1, 2, 3, 4, 5. So 5 data points, 5 random women from in there. Drop those 5 heights down, find the mean of it. So I've got a sample mean, a sample mean, a sample mean, and I'm going to create a whole new distribution of those sample means. Let's do it one more time with the animation here. I'm going to animate it again, 1, 2, 3, 4, 5, so that again I find the mean of those 5 data values and drop that mean down here. So I'm creating a new distribution of sample means, of means that I got from the sample. I'm going to do that 10,000 times. Instead of hitting it one at a time though, I'm going to literally do it 10,000 times all at once. So I'm going to hit that 10,000. See, notice so far I've done it 4 times, just individually. Now I'm going to do it 10,000 times. So I have 10,004 little means, sample means in here that I've created a new distribution of those sample means from that original data. Notice that this distribution has its own mean. Its own mean is at 15 and 95/100ths. Its median is there at 1600, and its standard deviation is at 2 and 27/100ths. I'm going to do it again 100,000 times just so that we've got a lot of data values here in our new distribution of sample means. There, I've done it 100,000 times. So I now have 110,004 different sample means where I've taken 5 women, found their heights, and then found the mean of those heights and dropped it down into this distribution. I'm going to record this data just so we have it later. So here we had a sample size 5. Our parent mean was still 16. Our parent standard deviation was still 5. That didn't change. But I had a sample size of 5 that I was drawing down each time. And when I did, the mean of my sampling, that's what we call this new distribution. We call it a sampling distribution. It's a sampling distribution of means. And the mean of it is 1599. So I'm going to put that 15 and 99/100ths in there. And then the standard deviation of this sampling distribution is 2 and 25/100ths. Okay, let's change our sample size. Let's change it and go back to 2. So right here, I'm going to change my sample size to 2. So instead of dropping down 5 women, I'm just going to choose 2 women. So if I do that, 1, 2, and find the mean. 1, 2, and find the mean. 1, 2, and find the mean. I'm going to do that 100,000 times. Ooh, there's a whole new distribution of those sample means. I've created a sampling distribution of sample means. But my sample this time was just sample size 2. Notice it still has that normal shape to it. But when we compare it to what we just did with the 5, hey, my mean of that sampling distribution is at 16. The median is also at 16. But notice the standard deviation of this thing is a little bit bigger than when the standard deviation, when my sample size was 5. Let's see what happens when I make my sample size 10. So in other words, I'm now going to pull 10 women's heights from my original population. Watch it go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to find the mean of those 10. I'm going to create a sampling distribution of those sample means. So here's a sample mean from this sample of 10. I found the mean, so that's a sample mean. I'm going to create a whole distribution of those sample means. So let's do that 100,000 times, where I drop down 10, find the mean. Just for fun, let's do it another 100,000 times. Notice it still has that fairly symmetric shape. It still looks pretty normal. Then let's look at the mean of this new sampling distribution. It too is right there at 1599. I'm going to write it down just for us to look at it again later. And then notice that the standard deviation this time got a little smaller. We're at 1 and 58/100ths. So our parent mean, though, didn't change, and our standard deviation from that parent distribution didn't change. Let's increase the sample size again. Let's increase it now to 16, and just see what happens when I increase it to 16. Does it change anything as that sample size gets larger? So I'm pulling out 16 women's heights from this parent population. I'm going to find the mean of these 16, and that mean goes there. I'm going to do that over and over and over again so that I create a whole new distribution of means, a whole new sampling distribution of means. Let's do it 100,000 times, maybe even 200,000 times. Notice again that that distribution is still approximately normal. Here, my mean is 16. My standard deviation, though, got even smaller. So it was 1 and 58 hundredths. Now we're at 1 and 25 hundredths. My parent, though, that mean and that standard deviation did not change. We'll do it one more time with this shape of normal, and then we'll try a different shape from our parent and just see what happens when we do that. So here, let's jump all the way down to 25 now. So in other words, I'm choosing 25 random women from this population distribution. And I'm going to find the mean of that data. I'm going to create a whole new sampling distribution of those sample means. So I'm going to do it 100,000 times, 200,000 times. When I do, here again, I have this nice symmetric shape to my new distribution. My mean right there at 16 still. But my standard deviation again got even smaller. Now it's only 1 is my standard deviation. So that data is getting closer and closer. The means, those sample means, are right in this little area, this tiny little distribution. They're not very spread out at all. And my parent mean and my standard deviation is still there at 5. So when my population was normal, notice that as my sample size increased, the mean of the distribution stayed right about 16. But look at that standard deviation of this sampling distribution. As my sample size increased, that standard deviation got smaller. Let's try it with a different shape and see if it changes anything. So this time, let's make the shape of our parent population skewed. So I'm just going to take this shape, this parent population, and let's make it skewed. So inside this little applet, it has this nice little animation, and we can change it around a little bit just to kind of look at this sampling distribution. And here's a skewed parent population. Notice that this one is skewed to the right. Those values over here on the right would pull our mean to the right, so it's skewed to the right. And let's see what happens when I do the same thing. So maybe this distribution is, I don't know, salaries, where most people make right in this this range. You know, they're right here, but you've got your supervisors, the people who've been there longer, your president, CEO, so they skew that salary distribution to the right. And let's start at our smallest sample size, where we're just choosing 2 employees and looking at their salaries. So I choose randomly 2 employees, and I find the mean of those 2 employees. And I do that over and over and over again. Find the mean of the data. Find the mean of the data. And I'm going to create a new distribution of those means. A sampling distribution of sample means. So I do it 100,000 times. 200,000 times. It's still pretty skewed to the right, isn't it? That distribution looks still skewed to the right. Maybe not as skewed as this one was, but it still looks skewed to the right. Let's record some information just so we can look at it here in a minute. So the parent of our skewed population has a mean of 8 and 800ths. And this parent has a standard deviation of 6 and 2200ths. Notice that the mean really is greater than the median. It shows us that it really is skewed to the right there. Let's look at our sampling distribution that we created of sample means. And the mean of that distribution is 8 and 800ths. And the standard deviation there is 4 and 4100ths. Let's do this with a larger sample size. Let's see if the same thing happens that happens before, where our standard deviation gets smaller. So I'm going to change my sample size to 5 now. And let's again pull 5 salaries, find the mean of those 5 salaries. Let's do that over and over and over again so that we create an entire sampling distribution of those sample means. So if I do 100,000 times, 200,000 times, I have a new sampling distribution of sample means. And if we look at that sampling distribution, my mean is still right there at 8 and 800ths. But my standard deviation now is at 2 and 7800ths. But my parent was still 8 and 800ths and 6 and 2200ths. So notice that when I increased my sample size, it really did get smaller, that standard deviation. Let's also look at the shape of this distribution. Notice that the shape of the distribution is not as skewed right as it was. It's getting more and more symmetric. Let's see if that continues if I make my sample size even larger. So now let's check a sample size of 10. So I'm pulling out 10 employee salaries. I'm going to find the mean of those 10 employees. I'm going to create an entire new sampling distribution of those sample means. I've done that 201 times. And notice in this new distribution, the sampling distribution of sample means, my mean of that sampling distribution is still 8 and 800ths. And the standard deviation is at 1 and 9700ths. It got smaller. And notice the shape of this. My mean and my median are getting really close to one another. So it's looking more and more normal, more and more symmetric. So the parent was still there at 8 800ths and 6 and 2200ths. Let's raise the sample size again. So I pull out 16, find the mean. I do that over and over again, create a new sampling distribution, and notice that it's even looking very symmetric. My mean of that new sampling distribution is still 8 800ths, and the standard deviation now is 1 and 5600ths. So again, we're just getting smaller and smaller with that standard deviation. In other words, my data is less and less spread out. It's getting closer and closer together. One last time with this skewed data, let's do it with a really large sample size of 25, so that I'm pulling out 25 different employees and their salaries. I'm going to find the mean of that data. I'm going to do that over and over again. So there's my sample mean. I'm going to create a new distribution of those sample means. Do that a couple of 100,000 times. And I now have 8 and 800ths. And my standard deviation is 1 and 2400ths. So notice that the shape of that is again very symmetric. So even though my parent population was really skewed to the right, as I found those sample means and created a new distribution of sample means, this new sampling distribution was approximately normal. It was looking more and more normal the larger my sample size. Cool. And my standard deviation, as my sample size increased, my standard deviation got smaller. Let's do this one more time, where I have the shape of the population, my parent population, is some custom. So I'm going to take this and I'm going to change my parent population to something that's custom. I'm going to draw some really weird distribution. I don't know what it is. I've collected data, and it's just really odd looking data where, I don't know, maybe it's I I have no clue. Some weird data where the data is just all over everywhere. That's a weird shape. Now, but I'm going to do the same thing. So here in this custom data, my mean of that distribution is at 17 and 31 hundredths, and my standard deviation is 10 and 78 hundredths. I'm going to take and start with just 2, where I take 2 random pieces of data and I find the mean of that. I'm going to do that 100,000 times. Well, when I do that with that really small distribution, really small sample size, this still looks fairly similar to its parent there. It's got a few more bumps in there, but it's still really, really weird looking data. Even at those, some weird looking data. So now I'm just going to record that sample mean. The mean though is still really close to its parent. And the standard deviation is at 7 and 63 hundredths. I'm going to raise my sample size to 5. So I'm now pulling out 5 of those data values and finding the mean of that. I'm going to do that 100,000 times, 200,000 times, and I'm going to look at this shape. Notice that it doesn't look as much like its parent as before. So as I increase that sample size, the means, this distribution of sample means, looks more and more symmetric, more and more normal. So let me record the information so we can look at it here in a second. So the mean of the distribution is 17 and 33 hundredths, and the standard deviation is 4 and 82 hundredths. Raise that sample size to 10, and we do the same thing where we pull out 10 of those data values, and then we find the sample mean, that mean of that sample. We're going to do that over and over again to create a distribution. And notice that that distribution is looking more symmetric. And the standard deviation is even smaller, so my data is getting closer. Those sample means, this sampling distribution has a smaller standard deviation. A couple more times, I'm going to do that with a sample size of 16. Create a sampling distribution of those sample means. Just write down our data here. So our mean of that new sampling distribution is still 17 and 31 hundredths. And our standard deviation is 2 and 69 hundredths. Parent mean is 17 and 31, and that didn't change. Then, one last time, let's make a really large, or the sample size of 25. Do that a couple of 100,000 times where I pull out that data, find the sample means. So notice that the mean of this sampling distribution is still the same mean as its parent, but the standard deviation of this sampling distribution has gotten even smaller. So a few things that we've noticed as we've done this. It turns out that no matter what my parent distribution is, when I pull out data, a sample of data, and I find a statistic from that data, in this case my statistic is a mean, I'm finding that sample mean, and I create a new distribution, a sampling distribution of that sample data, this new distribution is, as my sample size gets larger, this becomes more and more symmetric, or it approaches normal. And my mean of the distribution stays right about the same as the parent mean. Notice that the mean of our custom was about the same as the mean of the parent. The sampling distribution mean of our skewed was the same as the mean of the parent, and the mean of our normal was the same as the mean of our parent. But the standard deviation, as my sample size increases, the standard deviation for my sampling distribution decreases. Now I want to look for a minute just to see if we can figure out how this is decreasing, or what the ratio is or what's causing that decrease. We know that the sample size is helping with that decrease, or is causing some of that decrease, because as our sample size increases, we see that the standard deviation decrease. As our sample size increases, our standard deviation decreases. So what we're going to do is we're just going to find the square root of our sample size. So this square root of n, I'm just going to take the square root of this 2 and see what is the square root of 2. So on my little calculator, you can do it on your calculator, I'm just going to find the square root of 2, which is about 1.41. Then I'm going to find the square root of 5. So here I'm going to find the square root of 5 is 2.24. Then the square root of 10, if I do the square root of 10, then that's 3.16. We know the square root of 16 is 4, and we know the square root of 25 is 5. Now those same numbers will be true no matter what the shape of my distribution was, because the square root of these 2, 5, 10, 16, and 25 stay the same no matter what. I'm going to use this information here in just a second. So I'm just going to fill in this little chart to help me see this information. Now, what I'm going to do is I'm going to take my parent standard deviation and I'm going to divide it by this square root of my sample size, and I'm going to see what happens. So in this case, my parent standard deviation was 5, and I'm going to divide that 5 by this square root of n. So I'm taking 5 and dividing it by this 1.41. And I want to see what that is equal to. You can do this at home too. Just take out your calculator and do 5 divided by 1.41 and see what you get. I got 3.57. I'm going to do that for each one of these. In this case, my parent standard deviation was still 5. I'm going to divide that by the 2.24, and I'm going to see what that is equal to. So the standard deviation of 5, I'm dividing it by the square root of my n, which is the square root of 5, and I just want to see what that's equal to. 5 divided by 2.24, I got 2.23. 5 divided by standard deviation of the parent divided by the square root of 10 is 3.16. So if I do that division, then I get 1, that equals 1.58. I'm going to take 5 divided by the square root of 16, which is 4, and 5 divided by 4 should be 1.25, and then the standard deviation of 5 divided by the square root of 25 is 5, which equals 1. Now, I want you to notice when I did that. When I took the parent standard deviation and I divide that, I take that parent standard deviation and I divide it by the square root of my sample size. Notice this 3.57, this 2.23, this 1.58, 1.25, and this 1 show up really close on this other column. So when I take the parent standard deviation and divide it by the square root of my sample size, I get something really close to, or exactly, the standard deviation of that sampling distribution. Let's see if that works when my population was skewed. Is that going to be true for here as well? Let's test it out. I'm going to take that parent standard deviation of 6.22. I'm going to divide that by the square root of the sample size, in this case the square root of 2, which was 1.41. And when I do that division, 6.22 divided by 1.41, we get 4.41. Hey, that's the same as what our standard deviation of our sampling size was, our sampling distribution was. Let me try it again. 6.22 divided by 1.41. When I divide that, not 1.41 this time, but 2.24, because that's the square root of 5. When I divide that, 6.22 divided by 2.24, sure enough, we get 2.78. Wow, it really does turn out to be that standard deviation of the sampling distribution. We can do that for each one of them. I'll let you do it at home to test it to make sure that it works for all of them. But it should, if I do this division each time, I divide 1.97. I divide the parent standard deviation by the square root of that sample size. I should get the standard deviation of my sampling distribution. So this parent standard deviation divided by the square root of my sample size ends up being the equal to that standard deviation of the sampling distribution. So we have now discovered the central limit theorem. And the central limit theorem tells us these things. It says that when you have a population, no matter what that population of data is, that population distribution, when you pull out a sample from that distribution and you find a statistic from it and create a whole new distribution of those statistics, in this case sample means, when I create a sampling distribution, when my sample size is large enough, it does have to be large enough. So really we say it has to be at least 30. Now we were seeing some symmetric distributions even at smaller sample sizes. But we say that that sample size needs to be at least 30 to make sure that it's a nice normal distribution. So when we pull out a sample size of at least 30 and we find a sample statistic and create a sampling distribution, that sampling distribution will be approximately normal. The mean of that sampling distribution will be approximately the same as its parent, and the standard deviation of that sampling distribution will be the parent standard deviation divided by the square root of the sample size. Let's look at the central limit theorem and how we use it. So the central limit theorem tells us that for all populations with a mean, remember we represent the mean with that Greek letter mu, and a standard deviation where we represent the standard deviation with the Greek letter sigma, a sampling distribution of sample means will have three characteristics. If the sample size, where we represent the sample size with the letter n, is at least 30, or the population is normally distributed. So in other words, for whatever shape my population is, that distribution of my population data is, let's say the population data is skewed to the right, or my population data is skewed to the left, or maybe my population data has a nice normal distribution. No matter the shape, when I go into that population and I pull a sample and I find the mean of that sample, and then I pull another sample of the same size and I find a mean of that sample, and then I do that over and over again, and I create a whole new distribution of those sample means. Each one of those means I create a whole new distribution of. That new distribution will have these three characteristics. The first characteristic is the mean of that new distribution, that sampling distribution of sample means, the mean of that distribution will be about the same as the mean of my population. Then the standard deviation of that new distribution I've created, that sampling distribution, will be equal to the standard deviation of my population distribution divided by the square root of my sample size. And then the third characteristic is the shape of that new distribution, that sampling distribution of sample means, will approach normal. No matter the shape of that original distribution, it will approach normal. As long as my sample size is at least 30, or if my population is normally distributed to begin with. And then the larger the sample size, the closer to normal that sampling distribution is. So with that knowledge that this new sampling distribution of sample means has those three characteristics, we can begin to answer some questions about the sampling distribution after collecting a few samples. So here's an example. Some health reports claim that the mean duration of a cold is 7 days, with a standard deviation of 2 days. If samples of 100 people with colds are taken and the length of the cold is recorded, what would you expect the mean of the sampling distribution of sample means to be? Well, think about that for a second. In my population, people get colds, and the average cold is 7 days. Maybe some of them have less than that, they have more than that. Maybe that distribution is skewed to the right. And I go out into the population and I collect 100 people and I ask them to record how long their cold is. And then I do that all across the United States. I pull a sample of 100 people and I create a whole new distribution of sample means. I want to know what would I expect that mean of that distribution of sample means to be. And I know from the central limit theorem that the mean of my sampling distribution, so this is the symbol for the mean, and then this little X bar is because it's a distribution of sample means, should be equal to the population mean. Well, we know that our population mean was 7. So the mean of our new distribution will also be 7. What would you expect the standard deviation of sampling distribution of sample means? So what would I expect the standard deviation to be of this new distribution that we've created of sample means? Well, I know from the central limit theorem, again, sigma tells me I'm talking about standard deviation. This little X bar means that it's the standard deviation of the sampling mean of the sampling distribution of sample means. That should be equal to the standard deviation of my population distribution divided by the square root of my sample size. So here, my population standard deviation was 2 days. I'm going to divide that by the square root of my sample size, which is 100. So 2 divided by 100, the square root of 100, which is 10, is just equal to 2/10. I know that the standard deviation of this new sampling distribution is 2/10. So I know a little bit about my sampling distribution of sample means. I know that the mean should be about 7, and my standard deviation should be 2/10. And then I'll also know that it will have that nice bell-shaped curve, that normal distribution. And I can use some of my normal distribution rules, like the empirical rule, to help me to find probabilities within that. So let's use the fact that we know that this sampling distribution of sample means is approximately normal to find a probability. So here's an example of that. The same problem, some health reports claim that the mean duration of the cold is 7 days with a standard deviation of 2 days. If the sample of 100 people with cold is taken and the length of the cold is recorded, so we've got the same setup, but here at the end our question has changed. What's the probability the mean duration of that sample of 100 people, that mean, is between 6 6/10 and 7 4/10 days? So in other words, we've gone out and we've collected the duration of a cold from 100 different people. And we find a mean from that. And we want to know what is the probability that that mean is between 6 6/10 and 7 4/10 days. Well, we know that that mean belongs to this distribution of sample means. And we know that this distribution of sample means is approximately normal. So now we can use our normal information about the normal distribution to help us find that probability. So first thing I'm going to do is draw this distribution that sample mean belongs to. And that sample mean belongs to a distribution where, remember, right in the middle, I'm going to put this mean of 7. We expect the mean to be 7 because our population mean was 7. Then our standard deviation of that sampling distribution is 2/10. So I'm going to count up 2/10. So to 7 2/10, count up another 2/10. 7 4/10. I'm 2 standard deviations up one more standard deviation, and I'm up to 7 6/10. That's 3 standard deviations above the mean. If I count backwards, I'm at 6 8/10. That's 1 standard deviation below the mean. Count back 2 standard deviations below the mean, and we're at 6 6/10. And back 1 last deviation, and we're at 6 4/10. So this distribution of sample means we know is approximately normal. So we know its peak will be here at the mean, median, and mode will be about the same. And we know at each one of those standard deviations we have an inflection point, and it's symmetric. So both sides of our distribution should be approximately the same. We should be able to fold it. So I'm going to draw my bell-shaped curve here to show that normal distribution. And this sample mean that we've collected from this sample of 100 people falls somewhere in this distribution of sample means. And we want to know what's the probability that it is between 6.6 and 7.4. What's the probability that that mean falls somewhere in here in our distribution? Well, we know from the normal distribution and our empirical rule that 95% of our data falls within 2 standard deviations from the mean. And in this case, our 6.6 is 2 standard deviations below the mean, and our 7.4 is 2 standard deviations above the mean. So we've gone out 2 standard deviations, and we know from the empirical rule that 95% of the time, or 95% of my means will fall in that range, or 95% of the area underneath this curve is between 6.6 and 7.4. So we expect, or the probability that we get a mean from those 100 people that is somewhere in between there is 95%. This is what makes the central limit theorem so very powerful. The fact that we know that this distribution of sample means is approximately normal lets us know that the probability that the mean of this sample is between those two values is 95%. And because we know no matter what the distribution started with from our population, that new distribution of sample means will be approximately normal, we can use all of our information about normal curves to help us to find out about means of samples. So the central limit theorem is an extremely powerful theorem that we use in statistics. Let's use the central limit theorem to help us solve some problems. A researcher finds the mean price of a movie ticket in the United States is $10.20, and the standard deviation is 70 cents. So we're talking about the entire population of the United States, all the movie theaters there. The mean ticket price is $10.20, and the standard deviation is 70 cents. Sample means are calculated for samples of size 49. So we go out to movie theaters and we gather a sample of 49 movie theaters, and we collect all the prices, the ticket prices from those 49, and then we add them up and divide by 49, and we find the mean of that sample. And so we do that here. We found a mean. We find another sample of 49 movie theaters, find the mean of those tickets, and do that over and over again. And each one of those new sample means that we've created or that we've found, we use to create a new distribution of sample means. So we have a new collection of data that is just the sample means. And that distribution is what we're looking at. And we want to know what is the mean of that sampling distribution of sample means. So this new distribution that we've created of just sample means. What's the mean of it? What's the average of it? Well, the central limit theorem tells us that the average, the mean of our sampling distribution of sample means, remember that X bar is for the sample mean and the mu is for the mean. So the mean of our sample means is equal to the population mean. That's what the central limit theorem tells us. So that tells me that the mean of my new sampling distribution of sample means is equal to that same $10.20. Then I want to know what's the standard deviation of the sampling distribution of sample means. Well, again, the central limit theorem tells me that the standard deviation of the sample means is going to be equal to the standard deviation of the population. We're going to take that standard deviation from the whole population and divide it by the square root of the sample size. So in this case, my standard deviation of my entire population is 70 cents, 70 cents, and the sample size is 49. So I'm going to take the square root of 49. Now we just do a little math. That 70 cents is the same as 7/10. The square root of 49 is 7. 7/10 divided by 7. We'll just leave the decimal, and 7 goes into 7 one time. So it's our standard deviation there is going to be 1/10. So in our distribution that we've created of sample means, we know that the mean of that distribution is $10.20, and the standard deviation is 10 cents. We also know that it is approximately normal. The central limit theorem also tells us that our distribution is approximately normal. So if we were to draw that distribution, that sampling distribution of sample means, it would look something like this, with $10.20 right in the middle. And that $10.20 is going to be the peak of my distribution. It's going to be the mean, the median, and the mode of my distribution. Then the standard deviation is 10 cents or 1/10. So we're just going to count by that standard deviation. So I'm going to go up one standard deviation and I'm at $10.30. Count another standard deviation, I'm at $10.40. Count another standard deviation and I'm at $10.50. I'm going to count backwards as well, so I go below the mean or below average. 1/10 would be $10.10. Down another standard deviation and I'm at $10. And down one more, I'm at $9.90. Now this, because it's approximately normal, I know that each one of those standard deviation, there's an inflection point, and I also know that it's symmetric on both sides of my distribution will be the same. So it looks something like this, where I connect my little dots, and I have a normal distribution, a bell-shaped curve, where I've collected movie prices from groups of 49 movie theaters, found the mean of those movie theaters and put them on there, and that data looks something like this. Now, we're going to answer this next question using that information. A mean is calculated from a sample of 49 movie theaters. What is the probability the sample mean is less than $10? So we have gone out and gotten a sample of 49 movie theaters, found the mean of those movie theaters, and we want to know what's the probability that that sample mean, which is part of this distribution, it belongs here as part of that data. We want to know what's the probability that it's going to be $10 or less. So we're looking for this area under the curve. We're looking for that probability. How much of the area under the curve is there below $10? Well, because this is a nice normal distribution, we can use the empirical rule to help us. So let's do that. We know that 95% of our data, we know from the empirical rule that 68% of our data is within one standard deviation. We know that within 2 standard deviations is 95%, and that's kind of the one we need here, because this $10 is out 2 standard deviations. So we know that 95% of our curve is there within 2 standard deviations. Well, that means that since the whole distribution makes up 100% of our data, or 100% of the area under it, we know that on the outsides then, if we subtract off that 95%, then we have 5% on both ends. So I'm taking 100%, the entire distribution, and I'm subtracting off that 2 standard deviations, the empirical rule that tells us that 2 standard deviations, to get the 5% on the ends. But notice I don't need both ends. I'm not looking at this end, I'm just looking at that end. Because a normal distribution is symmetric, that means this side is the same as that side. So I'm going to split that 5% in half to find the percent there on that end. So I'm going to take 5% and divide it by 2, or split it in half, to get that 2.5%. So underneath the curve here, this is 2.5% of the area under the curve, or the probability that we get a sample mean that is less than $10 is only 2.5%. So there's the central limit theorem in a nutshell. The mean of your sampling distribution will be equal to the population mean. The standard deviation of your sampling distribution is the standard deviation divided by the square root of your sample size. And you can use the fact that it's a normal distribution to help you find the probability of where your mean, or what your mean will be. Let's use normal distribution and central limit theorem to solve a couple of problems. First, a population of 29-year-old males has a mean salary of $29,212 with a standard deviation of $2,120, and the distribution of the salaries is normally distributed. If a random 29-year-old male is selected from the group, what's the probability his salary is above $27,092? So this particular male that we're selecting from the group is part of this distribution of normally distributed data. So let's look at this distribution of data. first, we know that the mean of this distribution, which will be right in the middle, is 29,212. Remember that the mean is our peak of our normal distribution. It's where our mean, our median, and our mode sits. Then we know the standard deviation of this distribution is $2,120. So if I go up one standard deviation from that mean, I'm sitting at, well, we're going to add 2,120 to that. So we're at 31,322. Add another 2,120 to that. So then I'm at 33,442. So this is one standard deviation above the mean. This is two standard deviations above the mean. And if we go up one more standard deviation, then that third standard deviation, we're at 35,562. Then I'm going to go below the mean. So I'm going to subtract 2,120 from the mean each time. So that same distance, that same standard deviation, that same 2,120. Well, now we're at 27,100, or actually, when we go down 20, we need 8 more, so we're at 92. Then I'm going to go down another standard deviation from that. So down 2,000, let's go down 120 from that. Well, I'm going to need to break into my thousands there. So we're going to be at 20, bring down to 26, but then down 2 more, so we're at 24,000. And when I go down, I would be at, if I went down 100, I would be at 92. And I go down another 20, and I'm at 78. So 978. And if I go down one more standard deviation, down 2,000, I'm at 22,000. Down 100, you're at 858. So this is one standard deviation from the mean, this is 2 standard deviations from the mean, and this is 3 standard deviations from the mean. Remember, in that normal distribution, my peak is at my mean, and then it's symmetrically, it's symmetric on both sides. And so our dots should line up here, and at each one of my standard deviations, I have an inflection point, so that my normal distribution looks something, or this distribution of salaries looks something like that. And this 29-year-old male's salary is part of that distribution, and we want to know what's the probability that his is above this 27,092. So we want to know what's the probability his salary falls somewhere in there, or we're looking at the area under the curve from 27,092 above. And we know, because of the empirical rule, that if we go out one standard deviation from the mean, so between 27,092 to 31,322, 68% of our data falls within that range. We also know that above the mean, that above this halfway point, that half of our data, so from here to there is 68% of our data, and from here and above is 50% of our data. So half of our data falls in this area, falls above the mean. So if we just knew how much this was, I could add it to the 50% and find out that area under the mean, or find out the probability that his salary is in there. Well, because the normal distribution is symmetric, we can take and cut this piece in half. So half of 68 is 34. So 68% divided by 2 is 34%. That's between here and there is 34% of the area of the curve, or 34% of our data is going to be between 27,092 and 29,212. I'm going to add that to the 50%, that half on top, add it there, and I know that this area that I have colored, that 84% of our data is going to fall above 27,092. So, or the area under the curve is that much, or the probability that I choose someone randomly with that salary is 84%. So there, this was just a nice normal distribution. Let's change this problem up just a little bit. This time, we're going to take a sample of these 100 men. What is the probability that the sample mean salary is below 29,000? Notice that here, I'm not just pulling out one man from this distribution. Instead, what I'm doing is I'm pulling out 100 men, I'm collecting their salaries, and then I'm going to find a mean of those salaries. That sample mean is part of a new distribution. And we know that that distribution has a mean that is the same as the mean of our population. We know that from the central limit theorem. The central limit theorem tells me that the mean of this distribution of sample means, the mean of the distribution of sample means, is equal to the mean of our population. So in this case, the mean of this distribution, or these of sample means, is equal to 29,212. Then we know, because of the central limit theorem, that this sampling distribution of sample means, this distribution that this value belongs to, that the standard deviation of that distribution, of the sampling distribution of sample means, is equal to the standard deviation of our population divided by the square root of the sample size. So here I have the standard deviation is 2,120. We're dividing that by the square root of our sample size is 100. So the square root of 100. So we're really doing 2,120 divided by 10, which is just equal to 212. So we have this new distribution of sample means. This sample mean belongs to a new distribution of those sample means. And we know that one is also normally distributed. The central limit theorem tells me no matter what this distribution was, this distribution of sample means would be normally distributed. And so I can draw a picture of it as well. And we know that the mean of this distribution is 29,212. I'm going to do the same thing I did before, where I add on my 3 standard deviations. So I'm at 29,424, and then 29,636, and then 29,848. So notice that the standard deviation here is shrunk. In the standard deviation of our sampling distribution is smaller based upon that sample size. Depending, the bigger the sample size, the smaller your standard deviation. Then I'm going to go backwards. So that's up 3 standard deviations. I'm going to go back 3 standard deviations just to draw my distribution. And I'm sitting here at 29,000 even. If I subtract off 2012, well, now I'm at 28,000. Go down 200, I'm at 800, so 700 and a little more than 200. So I'm at 88. And then I'm going to go down another 212. So I'm still at 28,000, but now I'm at 576. So I just subtracted that 212 each time to get my standard deviations, or this one standard deviation below the mean, 2 standard deviations, and 3 standard deviations. Again, my mean is my peak. Mean, median, and mode are all the same in that normal distribution. It's nice and symmetrical. And then we've got our inflection points there. And as I draw my normal distribution here, this distribution is the distribution of sample means. So if I went around and collected 100 men from this population and asked them their salary and found the mean, that sample mean would be part of this distribution. Notice that there are 2 separate different distributions. This is the distribution of actual salaries from the men. This is the distribution of means that we have calculated from 100 salaries. So now we want to know what's the probability the sample mean is below $29,000. So if we look at this end, we're below that end. And there's a couple of different ways we could do it. Notice that this and that are complements of one another. You know, on this end, we've just figured out that this part, based upon that empirical rule, from here and above is 50%. So from here up is 50%. This little sliver is 34%. We just figured all that out right there. And so we know that 84% of my data falls within here. That means that if I take the whole curve, that 100%, and I subtract the 84%, I'm left with 16% in this area. So there's 16% of my data, or 16% of the curve. The area under the curve lies within this portion. So the probability that we get a salary, a mean, that sample mean salary is below 29,000 is 16%. So big difference here. Here I just collected one salary from one man. Here I collected a sample of 100 men, got a mean from that sample, and it was part of a new distribution. So when it was just normally distributed, I just used the numbers that we had to draw my distribution. But when I collected a sample, I had to figure out then my standard deviation for this new distribution. Let's use the normal distribution and central limit theorem to help us find z-scores. First, in an Oreo factory, the mass of a cookie is a normal distribution with a mean of 40 grams and a standard deviation of 2 grams. We want to know what is the z-score for a cookie that has a mass of 43 4/10 grams. So let's first look at this distribution that this cookie belongs to. So this population of cookies, if we were to weigh or find the mass of all of those cookies, we'd create a distribution. It would be a normal distribution with a mean of 40. So remember, our mean is here in the center. In a normal distribution, your mean, median, and mode are at the peak, at the right in the middle, and they're the high point. Then we can count by this standard deviation of 2 grams. So above the standard deviation, at 42 grams, that's one standard deviation above the mean. We say that the z-score of our mean is 0. We're right at the mean. The z-score for 42 is 1 because that's one standard deviation above the mean. I'm going to add another standard deviation on there so that we're sitting at 44 grams. That is 2 standard deviations above the mean, so we say that z-score is 2. I'm going to do that one more time, add a standard deviation, so add 2 on, and that z-score, or that is 3 standard deviations above the mean. Now I'm going to go below the mean. If I go count back 2, I'm sitting at 38 grams. This is 1 standard deviation below the mean. The z-score for this is a -1. That negative tells me that it is below the mean. It's below average, and it's 1 standard deviation below that average. Count back another 2 so that I'm at 36. The z-score for that 36 is a -2 because it's 2 standard deviations below the mean. And then 1 more standard deviation, and I'm at -3 because that's 3 standard deviations below my average. Now, if I wanted to draw this distribution, put in my inflection points there at my standard deviations, and remember that it's symmetric and it has this bell shape to it, so that the normal distribution looks something like this. And this particular cookie that we've randomly chosen from here has a mass of 43.4. That mass is somewhere in here. And we want to know what is the z-score, or how many standard deviations above or below the mean is this mass, this 43.4, that data value. Well, if I were to look on here, I can see that 43.4 would be somewhere in between here. 43 should be halfway, 0.4 a little bit over. So this is a data value that's somewhere in there. And I want to know, what's that z-score? How many standard deviations away from my mean is that? Well, it's 1 and a little bit. To find out more precisely, we can use that z-score formula that just says I take my data value, I subtract my mean, and I divide, so I find out this distance, and then I divide by this width, so I divide by my standard deviation. I'm going to do that here. My data value is that 43.4 grams. I'm going to subtract my mean to find out how far away it is, and I'm going to divide by this width of 2. We know that our z-score is going to be positive because our data value is above the mean, and it should end up being 1 and a little bit just by looking at where it's sitting. So let's see if it really is. 43.4 minus 40 is 3.4. That's that distance from here to there. Divide that by the width of 2. Well, 2 goes into 3 one time with 1 left over. My decimal remains. 2 goes into 14 7 times. So the z-score for that particular cookie is 1.7. In other words, this cookie is 1 7/10 standard deviations above average. Now, let's look at this. Here we have a sample of 64 cookies that was collected. The sample mean of 39 8/85 grams was collected. So, in other words, we collected 64 cookies, we found the mass of each of those cookies, and then we found a mean for those 64 masses, and that mean was 39 8/85 grams. We want to know what's the z-score for this sample mean mass of the 64 cookies. Now notice this is a different value than this data value over here. Here I am just looking at the mass of each cookie. Here I have collected a sample of 64 cookies, looked at those masses, and then found a mean of those masses. That mean is different from just a mass of a cookie. This mean belongs to a different distribution. Let's draw that distribution. Now we know from the central limit theorem that this distribution of sample means, called a sampling distribution, is also approximately normal. The central limit theorem tells us that it is going to be an approximately normal distribution. The central limit theorem also tells us that the mean of this sampling distribution of sample means, so the mean of this distribution of these sample means is equal to the mean of the population. So it's going to be equal to this same 40 grams. So here in the middle, my 40 grams is still my mean. That is also going to be the peak of this, just like it was before. My mean, median, and mode are right there in the middle. But my standard deviation for this sampling distribution of sample means is a little different. Remember that we take the population standard deviation and divide it by the square root of the sample size to find the standard deviation of our sampling distribution. That's what the central limit theorem tells us. So my standard deviation was 2 grams, and I'm going to divide that by the square root of my sample size of 64. So I have 2 divided by, well, the square root of 64 is 8, or that is 1/4, or maybe you could call that 25 hundredths. You could either just do 1/4, or you could call it 25, this is equal to 25 hundredths. 1/4 is 25 cents. So I'm going to count up by the standard deviations. So 40 and 25 hundredths grams is 1 standard deviation. So the z-score is 1 standard deviation above the mean, whereas my mean is z-score is 0. If I add another one of those, I'm at 40 and 5/10 or 50, 25 cents, 50, if you think money. So that z-score is 2 standard deviations above the mean. Add another 25 hundredths, and you're at 40 and 75 hundredths grams. And that is 3 standard deviations above the mean, so the z-score would be there at 3. I'm going to count backwards a standard deviation, so I'm subtracting 25 hundredths. So I'm at 39 and 75 hundredths. That's 1 standard deviation below the mean. To show that, I call that z equals a -1. That negative lets me know that we're below average. Then subtract another 25 hundredths off of there, and we're at 39.5. The z-score there would be at -2, because that's 2 standard deviations below the mean. And one more of those, and I'm at 39, 25 hundredths and 25 hundredths. And that's a -3 is its z-score. So the distribution that this particular sample mean belongs to looks something like this. We know it's normally distributed based upon the central limit theorem. We know that it has the same mean as its population, but that its standard deviation is smaller. So I want to know what's the z-score for this mass. Well, 39 and 85 hundredths, if I look at that, I can see that that particular data value would be somewhere between 39 and 75 hundredths and 40. Somewhere in here is that data value. And I want to know what is that z-score. Well, we can tell already that that z-score is going to be negative because it's below average. And that z-score should be less than 1 because it's not even 1 standard deviation below the mean. I'm going to use that same formula I used over here where I have x minus the mean. But notice that when I found the standard deviation here, the way I found that standard deviation was I took my population standard deviation and divided it by that sample size. So because I'm dealing with a sampling distribution, to find my standard deviation, I had to do the standard deviation divided by the square root of its sample size. So here I'm going to fill in. I have 39 and 85 hundredths is my data value. My mean was 40. And once I did this part, once I did this little formula, I found that my standard deviation was 25 hundredths. So now I do some subtraction. 39.85 minus 40. Remember, really, you're just doing 40 minus 39 and 85/100ths to get 0.15. But because this one's bigger and it's negative, it stays negative. Divided by 0.25. So now do a little more subtraction here. The way I like to do this is I like to just simplify my decimals or my fractions. First of all, if I'll multiply the top and the bottom by 100, I just end up with negative 15 over 25, and then I don't have to worry about those decimals. Then I'm just going to simplify my fraction. If I divide the top and the bottom both by 5 over 5, then I have negative 3 over 5. This fraction is the same as that fraction. Or to make it into a decimal, you could say times 4. Here I would have to do times 20 over 20. Either way, I'm going to get a negative, because it's negative, 0.6. So if we make that into a decimal, this would be the fraction if I wanted to count by fractions, or it's just a negative 0.6 or 6/10. Think of it as times 2, and you can see that better because that'd be tenths on the bottom and a negative 6. So negative 6/10. So the z-score for this one is negative 6/10. Notice that this one is closer to the mean. This z-score tells me that it's closer to the mean. It's below average because it's negative, whereas this one is further away from the mean. And we can see that it's further away from the mean. But because this one's positive, it's above average. So the z-score tells us a little bit about our data value. It specifically tells us how many standard deviations above or below the mean that data value is. And also notice that when it was just one cookie that I was pulling out, then that one cookie was part of this distribution, this normal distribution. But then when I pulled out a sample and found a mean from that, it created a sampling distribution. And in order to find that standard deviation, I had to take the standard deviation of my population and divide it by the square root of my sample size. So the central limit theorem is a really powerful theorem that lets us create these normal distributions using that information from our population. Math Made Simple is Simpson Math. Thanks for watching.